Okay. So today we're going to talk about sorted sets. Actually, first we're going to just recap a little bit about what we've done lately. And again, unfortunately, the book is very thin on this particular material. However, I think it's very important. And so I'm presenting it. So a simplified view of the Java collections framework is, I think this is at least sort of understandable of the basic idea. Just understand that the reality is a bit more complex. And if you look at the full Monty, it looks like a plate of spaghetti, just wires everywhere in boxes and stuff. But when you filter out what, in my experience, has been the main data structures that I've used, they are the array list and the linked list. And I talked about why you might want to use one or the other, depending on the context. Hash sets and linked hash sets. Again, the difference with the hash set is you don't care about the order. With a linked hash set, it'll keep it in the order that you put it in. The difference between a list and a set is that a list can have duplicates and a set cannot. So that's really the first bifurcation. The second difference, and an important one, is that with a list there is a specific sense of index. So a list is a generalization of an array with the added feature that it's expandable and contractible. So if I put 50 items into a list and I take 20 out, then I'm left with a list of size 30. Whereas with an array, a Java array is just very, very rigid. If I create an array of length 50 and I only set 30 of them, I still have an array of size 50. Whereas if I've used a list, then a list will expand or contract as I put things in or take things out. And like an array, though, I can access things by the index. So if I want to know if I have 50 items and I want to know what is the 33rd item, I can get the 33rd item. Or if I want to remove the 33rd item, I can remove the 33rd item. A set, a set has no real notion of that. Now with a linked hash set, you say, well, it has the order that I put them in, but there's no index. So even though with a linked hash set, I have the order that I put them in, if I say I want the 33rd element, I basically have to go through and iterate and count till the 33. I mean, you can do it, but it's not. If you want to access things by the index, then a set is not the right data structure to use. Okay, so that's hash set. With a hash set, I don't care about the order at all. And the main difference is that with a set, you can't have duplicates. Which brings the question of what is a duplicate? Okay, so it's important to understand the difference between an object reference and objects that are considered to be equal. I can have two objects with different object references, and I might want to consider them to be equal for the sake of things like putting them into sets or other kinds of things. The main example we've seen of this is strings. I can have two strings that are completely distinct objects. If they have exactly the same characters in them, then they're considered to be equal. Which kind of makes sense, except that that isn't given by default in Java. As we've seen with the playing cards, if we don't define an equals method and a hash code that explicitly overrides the one that's given in the object class, then distinct references to playing cards, even if they have the same suit and value, will not be considered the same thing. And as we've seen, and we'll probably see again, when we do that, when we say two playing cards are equal if their suit and their value are exactly the same, and we have a hash code which is also based only on the suit and the value, then they are considered equal. So I can put two distinct objects of playing card into a set, and if they have the same suit and the same value, we consider them to be the same. Okay, so all of that is review, but today we're going to look at sorted sets. Now, the thing about sorted sets, and this is something which comes up a lot, at least in my experience, is that we want to sort things. We want to keep things in a particular order. If we have numbers, we might want to keep them in ascending order, or we might want to keep them in descending order. If we have strings, we might want to keep them in the string order. And as we've seen, this natural string order is lexicographic, which is sort of almost alphabetic, but not quite. And we'll see how to, a question that may come up is, well, what if I want alphabetic and not lexicographic? And, well, hopefully we'll get to that. So again, just by review, the set interface, any implementation, it cannot contain duplicates, and that also applies to sorted sets, and sorted sets are sets. And there's no concept of an index. With a hash set, the order is arbitrary, whereas with a linked hash set, it kind of keeps them in the order that they're added, but still no duplicates. Where that usually comes up is when we're iterating through. So with a hash set, I just have a pile of things, and if I want to just kind of go through and list everything that's in there, then it'll come out in some arbitrary order, and we've kind of seen that. Whereas with the linked hash set, when I want to, say if I want to go through each of them in order, they will go through in the order that I put them in. Okay, so all of that by way of review. Now the sorted set interface is, we're going to kind of dip our toes a little bit into data structures. When I say dip our toe, I mean just very, 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 very lately. There are whole courses in this over in computer science. And back in the day, you would typically have two programming classes in a curriculum like this. In the first one, you'd learn the basics of the language. And then in the second one, you would spend the entire quarter learning about different data structures and actually implementing them from scratch yourself. For the purposes of this curriculum, the data structures course is somewhat moot, in the sense that there's no need for you to know the detail, all the gruesome details of what goes into that. And computer science academics write papers, and when they discover a new fancy way of keeping things in sorted order. So that's why the actual internal structure of what this is depends. What Java has done, Java has kind of taken what is considered to be more or less a really good data structure. It's called a red-black tree. There are, data structures, and you don't have to remember this, but like there are trees and there are heaps and there are treeps and all kinds of things that happen under the hood. all you need to know is just that in the case of Java's, it has an implementation called tree set. The name implies the fact that it's using a tree and is a set. And that's really all you need to know. When you're learning these things, the first thing you learn is something called a binary tree, and then the red-black trees are just sort of a slightly fancier way of doing that. And the reason that's important is that if you have just naive ways of trying to keep things in sorted order, like in other words, when you play cards and you're being dealt them and you sort them as you go, and that makes sense for a small number of cards. When you're dealing with many, many items, that's a terrible way to do it. And so generations of computer scientists and clever programmers have come up with different ways of doing this that's much faster, hence the tree thing. So internally, what the items actually aren't stored in the exact order, but they're stored in a way so that if you were to iterate through them, they would come out in order. So when we add to a sorted set, underneath it goes to a particular place, but from the user's perspective, all you need to know is that when I add an item, is it now the smallest item or is it not? That really is the only thing to be concerned about from the outside. In other words, the guarantee of the sorted set is that the smallest item is going to be, quote, at the top. So if you say, give me the first item, I want to know the smallest item in this set, it will always tell it to you. And if I want to iterate through the sorted set, it will always iterate through in that order that you've had. Now, in order to do this, every sorting algorithm is based upon a binary comparison. That is, and that's basically what you're doing. Again, think of how you kind of sort things. The basic operation is, if I have two of them, I need to be able to decide which one is bigger, or which one is smaller, or are they equal? Those are the only things that you need. And we've actually had a little peek into, with the playing card, that there is a there's a comparable interface, and if that's implemented, then the contract is to implement a compare to method that returns an integer and has an argument that's the other thing. And that integer that gets returned it returns a negative value if that other thing is smaller, and it returns a positive value if you're smaller, and it returns 0 if you're equal. So a tree set, again, a concrete implementation, it can only contain objects whose class implements the comparable interface. That's actually, there are two levels to this statement. So this is true at the first level, and there's just kind of mentally put a little bookmark on that statement because that's basically true and has an exception. So some examples are, well, all number types, because numbers have a natural ordering. If you give me two numbers, I can decide this one is bigger than that one, or that one is bigger than this one. The caveat on that is that I can only compare numbers that have the same type. In other words, if I have a sorted set that can contain integers, then I can't put a double on it. or a float. Now, if I have one that can contain doubles and I try to put an integer in, kind of underneath it promotes it to a double. We've seen promotion at the primitive level. And so what will typically happen if I have doubles, then I can put an integer on and it'll promote it. If you want to have integers, doubles, floats, whatever, there is a way of doing that we'll see, and that involves something called the number class. The number class is the superclass of all of the object wrappers. So, and we'll maybe see an example of that. Other example is string. So strings, what is the order? The order is lexicographic, have we seen. Two strings with the same characters exactly, up to case, are equal. Other than that, they're sorted in lexicographic order, which means that the UTF characters that are the non-alphabet alphanumeric ones are at the beginning, then all the capital letters, then all the lowercase letters. That's just the one to remember. That's the way it sorts it. Others, there are date objects and time objects, and these have a natural, I mean, how do you think you'd sort that? If I have two dates, is it obvious how I could decide which one is smaller than the other? Well, yeah, the thing to understand is that the format of the date is actually irrelevant for the actual object of the date. In other words, an objective type date may have a particular format, but the date that it refers to is irrelevant. That doesn't have anything to do with the format. In other words, today is February 2nd, 2022. So regardless of how I format that still refers to exactly the same day. And if I say is February 21st before or after that, then that's, even if it's a different format, then it would still be able to decide which one is greater or less than. But that's it. Yeah, that we're not going to get into that too much, but yeah, formatting dates and formatting times is an issue when that's actually something that I have to deal with the data that I deal with in the Navy, because a lot of things are date stamped, and you need to say, okay, what the heck is this date? What is the formatting? Java actually has a very rich set of formats that it can handle, and also output. And it has sort of a little mini language for dealing with that, because there are many, many different ways. Okay, so the tree set in its naked form, or in its basic form, it keeps the contents in sorted order according to the compare to method. And again, compare to returns -1 if this one comes before the other one, and 1 if the other one comes before this, and 0 if they're equal. I might have said that backwards a slide or two ago, so this is the correct one. Obviously, if this is a method which is implemented, and there are bad ways to implement it, and I have implemented many bad ones, but at the very basic, it needs to be consistent. So if A is less than B, then B must be less than A. Otherwise, I mean, if you're trying to figure things out, and if I have A in one hand and B in the other, and I say, oh, A is less than B, and then I switch them, and I say, oh, now that B is in my left hand, B is less than A. Well, that is obviously going to cause confusion. So, okay, so let's get to that in interface called Comparator. So there are two reasons why we might want to use to implement a class that implements the comparator interface. The first is, we might have a comparable class, but we want to keep them in a different order. So for example, the default number compared to sorts them in an increasing order. But if you say what if I wanted to keep them sorted in decreasing order? Well, I can't just do that automatically. I just have to do a little bit of extra work. I think I'll have time to show that. Or, and the second one, I don't have time today, but tomorrow I'll show you how we can have strings that are in alphabetic order. That takes a little bit more work, where we actually have to kind of delve into the guts of the strings a little bit. But if you find the lexicographic ordering a little bit weird, which I mean it is, face it. We're used to regular alphabetical ordering. Then you might want to do it some other way, and so we'll have to do a little bit of work. The other is something that we just encountered, is that what if I want to have objects in a particular class. That class does not implement comparable, and I don't want to edit that class. Remember, I have the class works absolutely perfectly. And remember, there's no, like surgery, there's no such thing as a trivial edit. And particularly adding an interface to something where I hadn't really anticipated before, that's kind of major surgery. Instead, what I can do is I can write a comparator interface that will take those objects and compare them according to the same rule that I've figured out. And that will basically do the same thing, except now the compare, as opposed to the compare to, it returns the same integer idea as before, but now I just give it a first and a second. And it's -1 if the first is less than the second, plus, well, 1 or negative value if the first is less than a second, positive value if the first is greater than the second, 0 if the first is equal to the second. And again, they need to be consistent in that if I reverse the arguments, then I get the same, then I get the negative of the other one. Okay, so here are some examples that I had planned. Let's